Welcome, my name is Daniel Ordonez and I will present our RSS paper on discrete symmetries of robotic systems, a data-driven and group-theoretic analysis. Our work studies morphological symmetries in locomoting systems. These symmetries are a prevalent characteristic in animal biology, intricately linked with the balanced distribution and replication of body parts. Our goal is to study these phenomena from a dynamical systems perspective, showing that these symmetries are also prevalent in the fields of robotics and computer graphics. We define a morphological symmetry as the capability that some dynamical systems have to imitate reflections, rotations, and translations of space with feasible discrete changes in the system state configuration. For instance, all bipedal systems have the capability to imitate reflections of space through feasible state transformations. While all reflections of space are unfeasible transformation, a morphological symmetry is always associated with a feasible state transformation. In other words, the system can always reach the symmetric state of a morphological symmetry. Another example of a morphological symmetry is the capability that some quadruped robots have to imitate 180 degrees rotations in space with a feasible discrete state transformation. In these scenarios, as both symmetry transformations are feasible, for each symmetric state, there exists more than a single kinematic configuration. The reason why we are interested in this type of symmetries is because they not only manifest in morphology but also extend to symmetries in the system dynamics, optimal control policies, and all proprioceptive and exteroceptive measurements. The symmetries in dynamics become apparent through the equivariant nature of the system equations of motion. Simply put, this implies that any set of motion trajectories originating from symmetric states will remain related by the symmetry transformation through time. For control systems, equivariant dynamics implies equivariant optimal control policies. As before, this implies that any set of optimally controlled trajectories originating from symmetric states will remain related by the symmetry transformation through time. Lastly, morphological symmetries extend to all proprioceptive and exteroceptive measurements. This implies that for any set of data measurements that we obtain from our robot or from the environment, there exists a set of symmetric measurements we can infer with no additional cost. This property applies to all relevant measurements in the fields of robotics, computer graphics, and computational biology. Our goal is to provide the theoretical abstractions required to generalize the concept of a morphological symmetry beyond the trivial reflection symmetry. Among the various systems we study with our proposed formalism, some quadruped robots stand out with a remarkable eightfold symmetry, meaning that for every system state there exist 7 different symmetric states. In practical terms, this implies that with the use of data augmentation, for every minute of recorded data during the robot operation, we can effectively obtain an additional 7 minutes of recording simply by exploiting the robot's symmetries. Moreover, morphological symmetry suggests that any learning task can be seamlessly translated across all symmetrical states. For instance, in the case of these quadruped robots, this implies that any mastered motion skill, be it walking or recovering from an arbitrary disturbance, can be applied regardless of the robot's forward direction, left-right orientation, or even if the robot is turned upside down. Consider the toy example of approximating a function that maps the state of a robotic system to some relevant quantity such as the contact state of the robot's feet. Because the robot has morphological symmetries, every symmetric state is associated with a symmetric contact state. This property of a function mapping symmetric input elements to symmetric output elements is known as equivariance. This is a highly relevant inductive bias when we desire to approximate such equivariant functions using machine learning models. In these cases, we can exploit symmetries either with data augmentation or through the use of equivariance constraints. Imposing equivariance constraints in machine learning models, such as neural network architectures, ensures that during all stages of learning, the model will respect the input and output symmetries. For our example, this means that when we feed the model with a set of symmetric states, the model output predictions will be related by a known symmetry transformation. In our paper, we show that imposing equivariance constraints on neural network architectures lead to a reduction in the number of trainable parameters that is proportional to the number of symmetries of the system. This while effectively enhancing the model's sample efficiency and generalization capabilities. We encourage you to read our paper to see the theory behind the intuition presented in this video and the empirical results of our experimental setups with real-world data.